So let's go ahead and start the second session of the day. Our first speaker is Alena Gusakov. Am I pronouncing that right?
Yeah.
Close enough. Good. Who's telling us about some work done in graph theory. I actually saw a archive paper like a day or two ago on this that came out of nowhere. Haven't had a chance to read it yet since I've been busy with all this, but I'm excited to. So yeah, let's hear about Hall's marriage theorem. Excellent.
All right. We formalized Hall's marriage theorem. This was joint work with me, Kyle Miller, and Bhavik Mehta. And I have a link to the archive paper as well here. What is this? Hall's marriage theorem is a standard part of the undergrad discrete math curriculum. It's not in MathLib yet, and we have the proof. We're currently working on integrating it into MathLib. So I'm going to give a brief outline of the talk. So we're going to present Hall's marriage theorem using a story about adopting dogs, and then three ways of formulating the theorem, the proof, a quick overview of it because it's kind of technical, and and then three ways of formalizing the theorem, and then our lean proof. So Hall's marriage theorem is typically introduced using a story about a group of boys and girls trying to find marriage partners, but we have a story that we think is a little bit more intuitive. So basically, you have a group of people that go to a dog shelter. They're looking for dogs to adopt. Each person has a list of dogs that they prefer, and every dog would be happy to go with any owner that chooses them. So Hall's marriage theorem gives us, or the problem asks for a necessary and sufficient condition so that every person takes home a dog. So we have three ways of formulating it. We have indexed families of finite sets, relations between types, and matchings in bipartite graphs. So indexed families of finite sets, for a fixed set S, a family of finite subsets indexed by a set I is a collection of subsets xi of S for each I and I. The set I is called the index set. An element X of all the xi is called a family of elements of the index family, and it may be regarded as a function from the index set into S with xi equals x of I with xi in xi for each I and I. A matching of an index family of subsets is a family of elements x that is injective when thought of as a function from I into S, which is to say that xi equals xj implies I equals j. So then Hall's marriage theorem says let xi be an index family of finite subsets with finite index set I, then the index family has a matching if and only if for all subsets j of I, we have that the cardinality of j is less than or equal to the union over the cardinality of the union of all the xi over I and j. Then the next formulation is for all sets, or for sets A and B, consider a relation R between A and B with R lowercase a, lowercase b, indicating that A and A is related to B and B by R. We could have picked better variable names, but so for a subset S of A, let R of S be the image of R of S in B. So the set of elements of B such that there exists some element in A that's related to the element in B. So given a relation R between sets A and B, a matching of R that saturates a subset S of A is an injective function from S into B that respects the relation R. So essentially R relates A to F of A for all A and S. A matching that saturates A is simply called a matching, or perfect matching, I should say. So let R be a relation between A and B. The relation has a matching that saturates A if and only if for all S subsets S of A, the cardinality of S is less than or equal to the cardinality of R of S. And now I'm going to give some definitions of simple graphs because we're currently developing the Simple Graph API in MATLAB. So I'm just gonna like give the definitions and then give the definitions that we have in MATLAB or working to integrate into MATLAB, so that you can see the parallels first. And then I'll talk about the statement of Hall's marriage theorem in this context. So a simple graph G on a set of vertices V is a symmetric irreflexive binary relation on V, where vertices, two vertices are adjacent if they're related by the relation. An edge of G is an unordered pair of adjacent vertices, so it's symmetric. And the set of all edges of G is denoted by E of G. The vertices comprising an edge, so if an edge is an unordered pair, a vertex, two vertices comprise an edge if they're contained in that unordered set. Those vertices are said to be incident to the edge. For subsets S of V, the neighborhood gamma of S is the set of all vertices in V adjacent to at least one vertex in S. So a matching on a graph G is a subset of the edge set such that the distinct edges of M share no incident vertices. The matching is said to saturate a subset W of V if every vertex of W is incident to an edge of M. The way we define bipartite graphs is with colorings, because a multipartite graph can be defined in terms of its mapping to a color set. So a proper coloring of a graph G with color set C is a function from the vertex set to C, assigning colors to each vertex such that the adjacent vertices have different colors. Or in other words, two vertices with the same color are not adjacent. So and then for a color in C, the color class associated to C is the preimage of F of C. A bipartition of a graph is a coloring of G with color set 1 and 2. So just partitioning into two sets where within the sets you have no adjacency, but between the sets you have adjacency. Let V1 and V2 respectively denote the color classes for colors 1 and 2. If a bipartition exists, then the graph is bipartite. Then Hall's marriage theorem says if G is a bipartite or bipartition simple graph with finite V1 and gamma of V finite for each vertex, or the neighborhood of the vertex for all the vertices is finite, then G has a matching that saturates V1 if and only if for all subsets of V1, the cardinality of those subsets are less than or equal to the cardinality of their neighborhoods. So then the proof, as mentioned, there's a lot. So I'll just give like a little point-by-point overview of how the typical proof goes. So the easy direction of the proof is if you have a matching that saturates A, then the cardinality of S for all subsets S of A is less than or equal to its neighborhood, the cardinality of its neighborhood. So it's clear that if you have a matching, or if you have an injective function between S or between A and B, then for all subsets of A, the cardinality of the neighborhood will be less than or equal to the neighborhood of S. Just because it's an injective function. So you're going to have at least that many vertices or elements in the neighborhood. And then the hard direction, we prove it using strong induction on the cardinality of A. So we have two base cases. We have the cardinality equals 0 and the cardinality equals 1. The empty set trivially has a matching. And if you have one element and the set for all subsets of A, where the cardinality of S is less than or equal to this cardinality of gamma of S, if A is just one element, then if the cardinality will be 1 and it's less than or equal to it's the cardinality of its neighborhood. So there's going to be at least one element in B that's related to A. So there does exist a matching. So our induction hypothesis, if R is a relation between a finite set A with A less than or equal to K and a finite set B, then if S, the cardinality of S is less than or equal to R of S, the cardinality of R of S for every subset of A, then there exists a matching of R that saturates A. So then our induction step, we're saying the cardinality of A is K plus 1. Then we split it off into two cases. So our condition is for every subset of A, the cardinality of the subset is less than or equal to the cardinality of its neighborhood, or the image of the relation. And we split that off into assuming for every non-empty subset S of A, we're saying that the cardinality of S is strictly less than the cardinality of R of S. And then the second case is there exists some subset S of A, or S naught of A, such that the cardinality of S naught is equal to the cardinality of R of S naught. And so, yeah, we can go over the full details of the proof in the social thing if anyone wants to go over it or hasn't seen it. So then 3 ways of formalizing. So this is the same 3 formulations, just now we're presenting how we did it in Lean. So with index families of finite sets, you have your relation alpha into fin set beta, iota. So then our matching is an injective function from alpha into beta that respects iota. And then Hall's marriage theorem is for all S fin set of alpha, or fin set over alpha, the cardinality of S is less than or equal to the union of the neighborhood of every element of S, if and only if there is a matching that saturates S, or saturates alpha. And then with relations between types, you have your relation between alpha and beta. We have our definition of the image of R. We define it as a filter for all B in the image. There exists an A and A such that A and B are related. Then Hall's marriage theorem is cardinality of A less than or equal to the image, if and only if there exists an injective function that respects the relation. It's the same thing over and over, just written differently. And then with bipartite graphs, here's our here are where we define things in Lean. These definitions parallel the definitions that I gave earlier. So we have simple graph over vertex set V is defined by an adjacency relation that is symmetric and irreflexive. Then the neighbor set of a vertex V is the set of vertices that are adjacent to V. The neighbor, so we're saying neighbor set image is the union for neighbor set image of a set of vertices is the set of vertices that is adjacent to at least one vertex in S. And then edge set, sim2V is the Cartesian product of V with itself modulo permutations. So it's that's the same thing as symmetric. So the edge set of graph is just the set of adjacent vertices within sim2V. So sim2V is just unordered pairs of all the vertices, and those unordered pairs are in the edge set, if they are in g.edge, where v to v is prop, v to v is true. And then our definition of bipartite graphs, we define again in terms of colorings. So a coloring is a mapping from V into a color set where two vertices are adjacent if and only if their color is not the same. Then the color set is the preimage for some color. And then a bipartition is a coloring where the color set is fin2 or 1, 2, 0, 1, 2 elements. Then our definition of matchings and matchings that saturate a set. We have a matching over a simple graph G is a set of edges that's a subset of the edge set of G, such that the endpoints of each edge are there's no overlap between the edges and the vertices. And then a matching saturates a set of vertices if S is a subset of all of the set of vertices in the edge sets or in the edges in M. So then Hall's marriage theorem in this context is for all S subset of the color set of 0, then we have the cardinality less than or equal to the neighbor set, if and only if there's a matching that saturates the color set 0. So our formalized proof, we're presenting the version with relations over types. So we have our image of our relation R, so R from alpha into beta, the image of R of A, or alpha, or R of A, where A is a fin set alpha, is the set of B in beta that is related to some A in our fin set. So we have our statement of Hall's marriage theorem, and then we have the easy direction, which is there is a matching or an injective function. If there's an injective function, it implies that the cardinality is less than or equal to the cardinality of the image of R of A. And then we have our two base cases, 0 and 1. We prove it using induction over the cardinality of alpha again, and we break it off. So we have our induction hypothesis less than or equal to n, and we break it off into the two cases for all non-empty proper subsets of alpha or fin sets over alpha. The cardinality of A is strictly less than the image of R of A, or the cardinality. And there exists some non-empty proper subset or fin set alpha such that its cardinality is equal to its image defined with respect to R. So, okay, yeah, that's pretty much it. These are just all the little main points of the proof. And I guess next steps, we have a proof of the countably infinite version of Hall's marriage theorem, and we want to use the category theory library to prove the full infinite Hall.
So sorry, what is the infinite? What's the infinite Hall one?
The countably infinite or the full infinite?
Either way. I don't know what either of the statements are. You didn't say, right?
Yeah, I didn't say. So the countably infinite version is alpha is countably infinite. And we still have fin set over alpha. Basically, the image of the fin set as defined by is going to be finite. Because if the image is infinite, then you run into the problem of not being able to. So if you have some element or if you have like some, if we go back to like the adopting dogs explanation, if you have some person who wants to adopt every single dog, then it's impossible for them to have some dog, because like if their entire list is like over the natural numbers, and then the next person wants the 0th dog, and then the next person wants the first dog, and then on and on and on, the person that wants every single dog will not get a dog. So yeah, you need it to be less than or equal to. And then the full infinite hull, not 100% sure. Gonna have to get back to you on that.
But can you deduce this stuff from the finite stuff using magic somehow?
I think you can. You might be able to if you have like the union of a bunch of fin sets, possibly.
There are compactness results that do it, I think.
Yeah, because I've seen this with coloring. You sometimes get stuff for free. Yeah, I'm just a bit rusty on. Sorry. Anyway, sorry to interrupt.
Oh, you're good. Yeah. So that's my talk. If anyone has questions, if anyone else has questions, yeah.
So thanks a lot, Alena. Round of applause.
I have a question.
Yeah.
So when you stated the theorem formally for graphs, you actually derived that after you do the proof for relations? So you have...
Sorry, continue.
You have the theorem stated for graphs in terms of existence of a bipartition and so on. That's done. Have you done Koenig's theorem?
We have, yeah. We have it in our paper, actually. I just don't have like the formalization here.
Okay.
Yeah.
I think that might be a nice way to see the full infinite version, because you can state Koenig's theorem without talking about the size of anything. Because you can just say there's a cover that sort of certifies that the matching is maximum.
Right. Yeah. Yeah. I just didn't include it because.
Right.
Yeah.
Right. Very nice.
You stated the theorem in 3 different ways. So then, firstly, you had to decide which one to prove, and secondly, you had to decide. That's it. You had to decide which one to prove. I guess once you proved one, you wanted to deduce all the others, right? So what went into the decision of which one you were going to prove, and how easy was it to deduce the other ones?
We just picked the simplest one, which is the one the relation between fin types. This one was just easier because you can supply it with any 2 fin types, and you can like, for the graph theory version, for example, the neighborhood of a set S in a vertex set is just going to be image rel. So like you can just basically plug in like all of the and the relation between alpha and beta is just going to be the adjacency relation of the simple graph. So this one was just the simplest one for us to prove, where we don't have to go through any like API.
Yeah.
We actually also directly proved the one for index sets. This one was just simpler to talk about. We mention it in the paper, and we go over that proof as well.
Thanks. And where's the PRs?
We're working on it.
On your last slide, you said something about possibly going to the category theory library to get the infinite version. Do you know sort of what direction through the library that's going, or is that?
We're still working that out because we kind of have to refactor things just a little bit, because this was kind of like a a last minute thing, because we were trying to make the experimental math deadline, and we did it in over the month of December. So we just like proved it, and now we have to go back and
So isn't it?
Sorry.
Are you able to use the axiom of choice? I'm new to the MathLib and Lean community and so forth. Are you able to use the axiom of choice at all in the MathLib?
Yeah.
Okay,
I guess.
So so once you shook your head, I knew what to do. So there's in Models and Ultra Products by Bell and Slomson, there's a proof of the general marriage theorem from this case that you just proved.
Mm.
And it uses the compactness theorem for first order predicate logic. No, for propositional logic.
Mm.
So it's equivalent to it's provable from the axiom of choice. That might not be, I'm not sure if it's equivalent, but it's provable from the axiom of choice because the compactness theorem for propositional logic is equivalent. It's equivalent to the Boolean prime filter theorem, which is a consequence of the axiom of choice.
Hmm.
So you don't have to go to the full strength of the axiom of choice, but you can use the axiom of choice to do it. Now, category theoretic proof of it, I don't know anything about that.
Yeah.
If you have some, or if any of you had something category theoretic in mind, I'd just be kind of curious to see in the future, because there are unfortunately few applications of the category theory library and the non-category theory parts of MATLAB. I think it would be neat to add to that.
Now, I wanted to point something else out to you, Alena. I've done work in topology, in metrics on hyperspaces, and it began as a theoretical work, and now I'm needing to do some computational things. And I think some of your approaches, some of the tools in your proof, in terms of nearest neighbors and so forth, can be used to enhance the computational aspects of calculating hyperspace metrics. And hyperspace metrics are used in computer vision, image analysis, and things like that.
Interesting.
Do you have any aspirations to more general graph matching theory and non-bipartite graphs like Tut-Berge?
Yep. Yeah, that's up next. Yeah.
Okay.
Sorry.
No, go ahead.
I was going to say, we are basically just trying to do like all of undergrad math or undergrad graph theory. So this just felt like a natural thing to start with, because defining matchings was pretty straightforward, and colorings and everything. But like we're gonna do stuff with trees. I've actually started defining like strongly regular graphs, because I really enjoy those. And yeah, we're just kind of going in all directions, and Tut's theorem is also one of those things.
Well, Hall's theorem is great because so many different things you can bootstrap off it to make an easier proof.
Yeah, exactly. Yeah, because it's like there are a bunch of different formulations of it, like within combinatorics. So it's like our fin type version just makes it really easy to just like plug in all of the different
Mm-hmm.
I don't really understand graph theory in some funny sense. We had this conversation, Peter and I were talking about this yesterday at the social. It's sort of astounding that we've done a huge chunk of an undergraduate degree in MathLib and yet never needed graphs at all, because they seem such a fundamental kind of object. But in some weird way, they don't form a category. This is one of the hypotheses that came up yesterday. People don't really talk about the category of graphs because...
Kevin, did you have any course in graph theory during your undergraduate education?
I did go to one, but it was somehow disjoint from all the other courses in some sense.
Yeah.
I think what's kind of ironic is that graphs have come up in various talks in the context of we have this dependency graph on types and extensions and so on. They're kind of an external object. You're not proving theorems about them. You're using them in a computer science way.
data structure.
Data structures, yeah. So I find it quite odd that these things haven't appeared at all yet. But maybe there's some profound reason behind it, because you can't define a morphism of graphs or something.
Yeah, I also, that's why I'm here to.
Yeah, it's great. It's great to see those slowly appearing.
If you formulate the notion of a graph as a model in model theory, then there's morphisms there.
Yeah, but is that the right notion? Right? I mean, somehow you can formulate the notion of a topological space somehow and then come up with a morphism, and it might not be the right, it might not be continuous. It might be an open map or something.
You have a nice category of graphs, and you have holomorphisms, and you have products, and they behave nicely. But for instance, there's a number of notions of product of graphs, and only one of them is a categorical product, and the other ones matter in other ways.
My comment, if I may, I think it's more a matter of taste. What appears in MathLib, it depends on the 126 people that have contributed so far, and it can quickly change.
It's good to see it changing now with the
yeah.
being at it. Yeah.
Maybe it's just coincidental. It's all some cultural thing.
I don't know if you've heard, but I've heard that there are people doing something maybe called analysis, and they don't care at all about categories and morphisms. It's a rumor.
I hear you can integrate 1 from 0 to 1 now, right?
So I think this is a fantastic discussion to. I was talking over somebody there. I think this is a great discussion to save for the next social break.